G'day, welcome to this video on continuity of functions, looking at it through a new light, which is the definition of epsilon and delta. This is a way of defining function continuity rigorously, and in this definition we can actually use it to prove a function is continuous from first principles without relying upon other definitions like the sum of continuous functions is continuous. We can actually just prove a function is continuous directly using the fact that this definition is how continuity is defined. So I guess a question for you, could you prove that f, a function that goes from 0 to infinity to the real numbers, and x goes to the square root of x is continuous? Could you prove that this is continuous from first principles without relying upon any other theorem except just the definition of continuity? That's something that we're going to look at in this video today. So what is the definition? Let D be a subset of Rk, a function that is mapping things from D to Rm, is continuous at at a element of D if, for all epsilon greater than 0, there exists delta greater than 0, such that x minus a less than delta implies that f of x minus f of a is less than epsilon. So let's unpack that a little bit. The idea here is to do with x minus a being less than delta is your input into the function is within delta of the value that you're looking at, x, and then f of x is within epsilon of f of a. So the idea is that as a converges to x, f of a is converging to f of x. And for any epsilon greater than 0, we need to prove in our proofs that there is some delta such that this implication here is true. F is discontinuous at x otherwise, and f is continuous if it is continuous at x for all x in D. Now, in a previous video, we looked at the definition of continuity using sequence convergence. That was definition 1. This is definition 2. And those definitions are logically equivalent. So if you prove one, you're also proving the other, and vice versa because of this logical equivalence. The sequence definition is useful when you want to disprove continuity because you can just find a counterexample that violates a sequence convergence definition. But this definition is useful for proving continuity, as you can rigorously prove the statement here to prove that the function is continuous. In the past, when I've been teaching this concept, I've noticed that people often struggle to understand conceptually what this actually is. So I just wanted to explore that a little bit intuitively to understand and hopefully appreciate why this definition is a rigorous definition of continuity. So let's look at this intuition down below. Now, if I were to graph a function f of x here, clearly we can see that it's continuous as it's just a very simple stroke of the pen. And applying the definition concept here is to pick a point x, or pick a point A here, and then look at the region around it that is within delta of this point here. So at A, if you're within delta of A, you can go plus delta over here or minus delta over here. Sorry for the scribbles, but you can go plus delta here, minus delta here, and you'll stay within this region of A. And what we want is that all of the function values of f in this region has to be within epsilon of f of A. And as we shrink down epsilon and we get closer and closer to 0, then we need our function around this point to be closer and closer to precisely being at f of A. And the idea is that if this didn't hold and there was some gap, like, well, actually I'll show you down below in a second. If it didn't hold, then you wouldn't be able to find f of a plus delta or a minus delta that is close enough to this tight box as epsilon shrinks down to f of a precisely. And this idea of having epsilon leeway above and below f of a and shrinking epsilon down to 0 and always having your function around a producing output that is closer and closer to this value is ensuring that there's no discontinuous jump, because this would basically catch out a discontinuous jump as it would violate the definition. Okay, so to take a look at an example of what I'm saying, this function here is not continuous. It has a discontinuous jump from here to here. And if you look at a minus delta, which is to the left of a here, you have f of that value being like this region. F of a minus delta is this value on the left of a here. And those values are all outside of being within epsilon of f of a. So being within epsilon of f of a means you must be in this red box. And here, no matter what delta we pick, we'll never be able to get values of a minus delta that plugged into the function will be inside this red box. So therefore, there does not exist a delta where being within delta of a from the left will give us that you're within epsilon of the function value at that value in a. When you're looking at this definition here, sometimes people focus on x or a and then swap around their focus, where this could be x element of d, and it's really the same thing definition wise, so just also watch out for that. Okay, hopefully that gives you a little bit of intuition as to why this definition is a rigorous way of defining continuity. And interestingly, when you're doing proofs on this type of thing, it can actually be pretty difficult, because you need to come up with a delta in response to every possible epsilon that will satisfy this definition here. So the best way to learn about that, I would say, is to do an example. So let's take a look. Let's have a go at doing this question together. Okay, I'll leave it there as some inspiration for us, at least for now. So let's go ahead and do this. With these types of proofs, you want to have some type of scratch work that helps us determine what delta we can pick in response to an epsilon that will satisfy the definition. So maybe we can just start off by rewriting the definition as something that we're wanting to show. We're wanting to show that for all a in our domain, there exists some delta. Oh, sorry. For all a in our domain, and for all epsilon greater than 0, there exists some delta such that x minus a less than delta implies that f of x minus f of a is less than epsilon. So for all epsilon greater than 0 and all a in your domain that satisfies x minus a less than delta, that will imply that f of x minus f of a is less than epsilon. Okay, so let's just take a look at this part over here. Consider f of x minus f of a, which is equal to the square root of x minus the square root of a. And we want to show that that is less than epsilon if x minus a is less than delta. So if x minus a is less than delta, this is less than epsilon. Okay, so let's unpack this more and see if we can prove that if this is true, so is this. Okay, so left-hand side is equal to, so focusing on this as what I mean by left-hand side, is square root of x minus the square root of a. And what I want to do is rationalize this. So I'm going to multiply it by 1, but represent 1 as a fraction that will rationalize this here. Okay, and the reason why I know to do this is because I know I can control x minus a. So my goal is to manipulate this here into something that contains x minus a, and then I can use that to prove that this is less than epsilon based on how this relates to delta, which you'll see in a second. So expanding this out, we get x minus a divided by the square root of x plus the square root of a. Okay, and then I can factor out what I really want, which is this, and then leave behind this. And I know that this here is less than delta. So if this is equal to this thing multiplied by x minus a, and x minus a is less than delta, then this whole expression will be less than delta multiplied by 1 divided by root x plus root a. And the thing about epsilon delta proofs is that we can control what the delta is in response to what epsilon is. So for all values epsilon greater than 0, there exists a delta. That means that if epsilon is equal to an arbitrary value, then we can choose delta to respond to that. So right now, if we could get rid of this and then we just chose delta to be equal to epsilon, we'd be done. Because the next step would be therefore this whole thing is less than epsilon as delta is equal to epsilon. But for now, we need to get rid of this in an inequality setting. So let's think about what this is. It's 1 divided by the square root of x plus the square root of a. How can we manipulate that to get rid of it? Well, we know that the square root of x is always going to be the square root of 0 or higher, because our function has a domain that is 0 or higher, which means that this will be less than or equal to delta multiplied by 1 on the square root of a. So essentially what I've done is I have I've decreased the denominator, which has increased the overall fraction, and that makes the step before smaller than this one. So if you follow that logic, I have decreased the denominator, increasing the whole fraction, and therefore making this whole thing less than this one. Sorry, this whole thing more than this one, or reading it this direction, this is less than or equal to this one. Okay, and I can almost do the same thing here in terms of just removing the a. Actually, no, I don't even need to remove the a. The other thing is that we have epsilon being chosen first, and then a and x being determined by this relationship here. So actually I would remove this part here and just say for all epsilon greater than 0, there exists delta such that, okay, there exists delta greater than 0 to be technical as well, such that x minus a less than delta and x and a being 0 and infinity, being a member of the set 0 to infinity, implies this. So I can choose my delta in response to both epsilon and a. So here, so long as a is not 0, I can just choose delta to be equal to epsilon multiplied by root a. choose delta to be root a multiplied by epsilon. And that is for if a is not 0. If a is equal to 0, then we can't do this because we cannot have delta equal to 0. Delta must be strictly greater than 0. Okay, so conceptually the idea is that we're focusing on proving that the function is continuous at a, and at this exact point a, we want to show that for all epsilon greater than 0, there exists a delta that will satisfy the definition. So actually that I could have left that there, what I just rubbed out. Anyway, good thing this is scratch work. Let's also work out what we should choose if a was equal to 0, because this won't work if a is not 0. Consider a equal to 0. We want to show that x minus 0 is less than delta, implies that the square root of x minus the square root of 0 is less than epsilon. So here I'm just plugging in a being equal to 0 because we're specifically looking at that point. So we have the square root of the absolute values of x less than delta, and this is what we want to show, implies that the square root of x is less than epsilon. So we need x being less than 0 to imply the square root of x being less than epsilon, which is that x is less than epsilon squared. And x in this context is going to be at most delta away from a. So if we choose delta to be epsilon squared, then we can ensure that x is going to be always less than epsilon squared, because x is going to be between 0 plus delta. And it doesn't include that point there. And if we choose delta to be epsilon squared, then we know that x that belongs to this region will always be smaller than epsilon squared. So choose delta equal to epsilon squared. So x being less than delta implies that x is less than epsilon squared, which implies that the square root of x is less than the square root of epsilon squared, which is just epsilon. Okay, so now we've got the scratch work. If a is equal to 0, we want to choose this. If a is not equal to 0, we want to choose this. And notice how messy this is as scratch work. It very literally is scratch work for this reason. We've come up with our plan of attack for this proof, where we now know for a specific a part of the domain, we can now prove that for every epsilon greater than 0, there exists a delta such that x minus a less than delta implies that. So now what we want to do is actually formalize this answer in our proof. And I'll walk you through the more pretty version of writing this out, and that'll finish our video on this. Okay, so prove that f is continuous. Oh wait, wrong sheet. This one here. Here's our proof. First, consider a belonging to 0 to infinity. Notice that we don't include 0, there's no hard bracket here, because we're going to do a separate proof for when a is equal to 0. Okay, let epsilon be greater than 0. And then choose delta equal to epsilon multiplied by the square root of a. Notice that delta is definitely greater than 0, as epsilon and a have to be greater than 0 as well from this, right? So we're essentially establishing our premise. If I were to get out this, we're establishing our premise where a is in our domain, and that every epsilon greater than 0 will satisfy this thing here. And we need to prove this is true for all a in the domain, and we're going to do that by separating the domain into this and then also showing it's true for a equal to 0, which together is the whole domain. Okay, so we're trying to establish our premise, and that is done formally through this. Okay, then for all x belonging to our domain with the absolute value of x minus a being less than delta, we have this. And remember, our goal is to show that given our premise here, that will imply that this is strictly less than epsilon. Okay, so that's equal to the square root of x minus the square root of a. As we showed before, that's equal to this. And then we know that this is less than delta because delta here is defined, where is it? As this. There you go. Those things, oh, sorry, you can't see. Those things together is what allows us to take x minus a in absolute values to be just strictly less than delta multiplied by this. This is strictly less than this. So this multiplied by this is strictly less than this multiplied by this when we're dealing with all these positive numbers here. Okay, and then we can get rid of the square root of x in the denominator here because we know the square root of x is positive. And then we can plug in delta being chosen to be epsilon times the square root of a. From our scratch work, we know that's a good idea because that is exactly equal to epsilon. And now we have in this chain, the left-hand side is strictly less than epsilon. Because this is equal to this, blah, blah, blah. Strictly less than this, less than or equal this. So if you line them all up, you get this is less than epsilon. Therefore, we've proven for all epsilon greater than 0, there exists a delta greater than 0, such that being within delta of x, being within delta of a implies that you are within epsilon of f of a, and therefore f is continuous for all these points here. And then to complete our proof, we want to show this is also true for a equal to 0, as in this definition. And from our scratch work, we know to choose delta equal to epsilon squared. And for all x being inside of 0 to infinity with x minus 0 less than delta, we have this. F of x minus f of 0 is just equal to absolute value square root of x, which is equal to this, epsilon. And therefore we have this is less than epsilon. And then we have shown that it's true for a equal to 0. And then these two together show that therefore f is continuous as a function for all a in 0 to infinity, which means it's continuous as a function overall. Okay, so that concludes our video on the epsilon delta definition of continuity, which is useful for proving functions are continuous from their first principles. Thanks for watching this video. I hope you found it helpful.